Students, in the previous video we discussed what is the force experienced by a charged particle when it is placed in a uniform magnetic field. We derived the equation as F is equal to Q into V cross B. So, whenever a charged particle moves in a magnetic field, it is experiencing a force. In this video, we are going to see after experiencing the force, what is the type of motion executed by the particle. So, imagine first case in which the initial velocity of the particle is parallel to the field. Particle is travelling parallel to the field. Imagine there is a magnetic field along the x-axis. Okay, and the particle enters the field parallel to the parallel to it with the velocity v. Now, if you look into this diagram, you can see the angle between B and V is 0 degree. So, here theta is equal to 0 degree. So, the force experienced by the particle is given by F is equal to Q into V cross B or Q VB sin theta, which is equal to 0 since sin theta is equal to sin 0 equal to 0. So, whenever particle is entering parallel to the field, it won't experience any force and it travels along the same path. There won't be any alteration in its path, it will travel in the same path with the same speed. Okay. Next, we are going to see what is the force experienced by the charged particle when it enters perpendicular to the field. Imagine you have a field along the z-axis . I am putting cross marks so that you can understand the field is into the plane of the board, and a particle is entering this field perpendicular to it like this with the velocity v. So, what happens when a particle enters perpendicular to the field? It experiences a force F is equal to Q V B sin theta. Your value of theta will be equal to 90 degree. Why? Because the field and the velocity are perpendicular to each other. So, we get F is equal to Q V B, and this is the maximum force experienced by the charged particle in an external field. So, let us see what will be the direction of the resulting force. For that, you have to use the Fleming's left hand rule. So, in our case, field is into the board and the particle is moving along this direction. So, what happens? Force is acting upward. Imagine you are travelling in a straight line, or a particle is travelling in a straight line. All of a sudden, a force is given in the upward direction. What happens? The particle starts to get deflected. The same way, so velocity in this direction, magnetic field in the positive direction, force will act along the upward direction, and this force will deflect the particle. Force will deflect the particle in the upward direction. When the particle reaches at this point, what happens? Again, force acts on it, it gets deflected. At this point, again it gets deflected, again it will get deflected, and the direction of force will be like this in each case. So, at the end, the particle will start to move in a circular path with the force into the center of the circle. So, whenever a particle is travelling perpendicular to the field, it experiences the maximum force, and this force will deflect the particle, and the particle will start to move in a circular path with the force towards the center of a circle. So, So you know, if the force is acting towards the center of circle, it will be centripetal force, which means our magnetic field is providing a centripetal force to the particle, and the particle will move in a circular path. So in our case, the magnetic force, that is QVB, provides a centripetal force, and the equation for centripetal force is mv square divided by r, or the radius of the particle in the circular path is given by r is equal to mv divided by qb. Now this is the expression for radius of the particle in the circular path traveling in the magnetic field. Now if you look into this equation, you can see m is proportional to v, m, q, inverse proportional to q and b. But you know, charge of the particle is constant. The field we are applying is uniform field. It will also have a constant value. M is also constant. So what is changing here? V is changing in direction. So we can say R is proportional to m, v or v, or R is proportional to the momentum of the particle. So greater the momentum experience, greater the momentum of the particle, greater will be the radius of the charged particle in the external magnetic field. Now let's see what is the frequency of the particle. You know what is frequency? It is number of revolutions or number of oscillations in a second. So we are going to derive next. We got the equation for radius. We are going to find out what is the radius of the, frequency of the particle. We have studied the expression last year. V is equal to R omega, or V is equal to R into, instead of omega we can write 2 pi f. On rearranging we get frequency f is equal to V divided by R into 2 pi. Now we know what is the value of R, what is the radius of our circular path. It is equal to mv divided by qb. So we get f is equal to V divided by mv divided by qb into 2 pi. On rearranging we get f, frequency of the charged particle, is equal to qb divided by 2 pi m. So the frequency of the charged particle executing circular motion is given by, in a magnetic field is given by f is equal to qb divided by 2 pi m, and this frequency is also known by the name cyclotron frequency. And is denoted by the letter F suffix C. So cyclotron frequency is equal to qb divided by 2 pi m. Next, we are going to see what is the time period of revolution. Now, the relation between frequency and time period is T is equal to 1 by F. So we can write T is equal to 2 pi m divided by qb. So if you look into this equation of time period and frequency, you can see f is depending on q, b and 2 pi and m. T is depending also on 2 pi m by q and b. All these are constant terms. So which means frequency and time period for a particle executing circular motion in an external magnetic field will not change. It will be a constant value since q, b, 2 pi m, all these are constant. Okay. Next, let us go to the third case. If the particle enters the field at an arbitrary angle, which means if the particle is entering at an angle, not parallel to the field, not perpendicular to the field, but at an angle. So imagine you have a field which is acting along the uniform field. Okay. Which is acting along the x direction, and the particle enters the field at an angle, the velocity v, at an angle theta. So this v is the velocity of a particle and it enters the field at an angle theta. What you can do, you can resolve your velocity into two components. One is perpendicular to the field and one is parallel to the field, and the perpendicular component will be v sin theta and the parallel component will be v cos theta. So we are resolving the components into two, v cos theta and v sin theta. So now consider the initial two cases. The case in which the particle is entering parallel to the field. In our case, we have a component which is parallel to the field, that is v cos theta. Now what happens when the particle enters parallel to the field? It won't be experiencing any force. Why? Theta is equal to 0 degree. So it won't experience any force, and as a result what happens? It will travel along the same path without any alteration in its path. Whereas if the particle is entering perpendicular to the field, what happens? It experiences a maximum force, and this force will, what will it do? It will make the particle move in a circular path. So you are traveling in a straight line. Imagine you are traveling in a straight line. One of the friend tried to make you move along the straight line, gave you a force from the back and made you move along the straight line, while one of your other friend is trying to make you move along a circular path. So what will be your motion at the end? You will be moving in a helical path like this. It won't be straight or it won't be circular, but an helical path, a spiral path. So whenever a particle enters a field at an angle, what happens? The motion or the path followed by the particle will be helical. Okay. Next we are going to see, so we have two components there, v cos theta and v sin theta. We are going to find out what is the radius of the particle, what is the path distance traveled in one complete revolution, etc. So first we take the perpendicular component of velocity. Equal to v sin theta. So this perpendicular component makes what? It makes the particle move along a circular path. So circular path means it will be having a radius, and equation for radius is r is equal to mv divided by qb. In our case, v is v perpendicular. So the equation becomes r is equal to mv sin theta divided by qb, and the time period of revolution t is equal to 2 pi m divided by qb. Why? Because time period is independent of r or v. So there won't be any change, it will be a constant value. Okay, next we are going to find out what is the distance travelled by the particle in one complete rotation. It is a spiral path, and this much distance travelled in one complete rotation is what we call pitch. We are going to find out what is the value of pitch for the charged particle. for the parallel component of velocity. B parallel. We have studied in lower class the equation speed is equal to distance by time. In our case, the speed is the parallel component, that is v cos theta. So, v cos theta is equal to distance. What is the distance called here? It is called by the name pitch. So, divided by time. Now, what is the time taken for one complete revolution known as? It is known as the time period. We can write v cos theta is equal to pitch divided by, what is the time period equation? 2 pi m 2 pi m by qb, or on rearranging we get pitch is equal to qb v cos theta divided by 2 pi m. This is the distance travelled by a charged particle entering the external field at an angle theta to qb v cos theta divided by 2 pi m. Okay. So, we discussed what is the motion of the particle when it is entering in a uniform magnetic field. Next, we are going to see what will be the force experience. We know what is the equation to find the force experienced by the charged particle when it moves in a combined electric and magnetic field, and that force is known by the name Lorentz force. Now, we are going to see the effect or motion of the charged particle in a combined electric and magnetic field. In our case, we are applying the electric and magnetic field perpendicular to each other. So, it is also known by the name cross field. If electric field and magnetic field are perpendicular to each other, it is known by the name cross field. So, imagine you have a field, electric field applied along the positive y axis and a magnetic field is applied along the positive z axis, and the charge is moving with the velocity v along the x axis. So, in chapter 1 you have studied when a charged particle moves in an external field, it experiences a force given by F is equal to QE in the direction of force, which means the force exerted by the charge external electric field on the charged particle will be along the y axis itself. Next, we are going to find out what is the direction of field what is the direction of force exerted by the magnetic field on the charged particle. So that what you have to do, you have to use the Fleming's left hand rule. In our case, the particle is moving in the positive x axis with the velocity v, and the field is pointing towards you with the magnitude b. So, the force will be acting perpendicular to both v and b, that will be acting downwards. So, our force will be acting downwards along the negative y axis. The magnitude F is equal to Q V B sin 90. So, sin 90 is 1. So, if M is equal to Q V B. So, electric field will be applying a field along the positive y axis, whereas the magnetic field will be applying a force along the negative y axis. Now, the force on a charged particle in a combined electric and magnetic field is given by F is equal to, total force is equal to Q E plus Q into V cross B. Now, our field, electric field is along the y direction. So, I am going to use unit vector J. Our magnetic field is along the positive z direction. So, I am use the vector K, unit vector K, and the velocity is along the positive x direction. So, I am going to use it, represent it using the unit vector I. And you know, I cross J, two vectors perpendicular to each other means the resultant will be perpendicular to both the vectors. Here it is I cross K, not K cross I. So, the resultant will be along the minus y axis or the minus J direction. So, we can write this equation as QEJ plus Q into VB, the direction minus J, equal to Q into E minus VB into J. Now, imagine a condition in which I am adjusting my magnitude of electric field and magnitude of magnetic field in such a way that the net force acting on the particle is equal to 0. So, condition in which the electric field and magnetic field is adjusted in such a way that net force is equal to 0. So, we can write this equation as Q into E minus VB into J is equal to 0, or QE is equal to QVB, or E by B is equal to V. This equation is known by the name velocity selector. Now, why is because, just look into this diagram. I have applied a field along the y direction from positive to negative. Is my field, it's pointing upward, and the magnetic field is along the z direction, it is pointing towards you. Okay, and a particle is entering the field. Now, when the particle enters a field, what happens? The electric field will execute a force QE. The magnetic field will execute a force on the charged particle QVB. Now, depending upon the magnitude, which force is having more magnitude, what happens? The particle will get deflected. If electric field is providing more force, then the positive charged particle will move to the negative side, that is towards upwards. And if the magnitude of B is greater, what happens? The particle will get deflected downwards. If I am adjusting the value of E and B in such a way that the net force executed by them is equal, what happens? Both are trying to pull the equal force. So, the particle will travel along the same path without any alteration. And this method is used, is known by the name velocity selector. Why? Because imagine you have a beam of particles traveling with, beam of ions traveling with different velocities. Okay. Now, you want to select a particular velocity particle ion from that beam. What must you do? You adjust your electric field and magnetic field in such a way that the value V is equal to E by B, so that the force exerted will be equal, and only those particles will travel along the same path, and you can collect those particles, and hence the name velocity selector. I hope you understood this topic. Thank you.